Let's look at this Calc 1 section from 2.6 and have a little review. By a theorem, if r is bigger than 0 and it is a rational number, then the limit as x approaches infinity of 1 over x to the r is equal to 0. That is if x to the r is defined for all x. So that workhorse definition or workhorse theorem is extremely valuable when we're dealing with limits of infinity. So for example, if I wanted to evaluate the limit as x approaches infinity of 3x squared minus 5 divided by 5x squared plus 4x, well, it's not readily available to me whether or not what's going on with that limit. And so sometimes people will teach some tricks and try to sort of understand what's happening with the limit, but you know, I like to approach things with mathematical rigor, and so I'm going to use this definition or this theorem to show what this limit is or understand if it doesn't exist. So remember something in mathematics. If I have a over b and I multiply both top and bottom by the same number, so c over c, I'm really multiplying by 1, right? A over b is being multiplied by 1. It's just a strange looking 1, and so it doesn't change its value. So what I want to do is pick a 1 to multiply both top and bottom of this rational expression. And our books suggest to us that we pick the biggest power in the denominator. So in this case, x squared. Now, sometimes and under certain circumstances you want to maybe pick a different number, but in this case we will pick the x squared. So let's just work that out. The limit as x approaches infinity of 3x squared minus 5 divided by 5x squared plus 4x. And then I'm going to multiply both top and bottom by 1 over x squared. And the reason I've done that is because I'm trying to get some things to cancel so that I can use this definition. This definition. And the concept here is I have multiplied both top and bottom by 1 over x squared, so I'm really multiplying by a c over c, which is really just 1. So algebraically, I haven't changed the value of anything. So then that simplifies to the limit as x approaches infinity of, so this would be 3 minus 5 over x squared, all divided by 5x squared divided by x squared, so that's just 5, plus 4 over x. Now I've done some of that algebra in my head for the most part. So 3x squared divided by 1x squared, or multiplied by 1x squared, is just 3. And minus 5 times 1 over x squared is minus 5 over x squared. And 5x squared multiplied by 1 over x squared is 5. And 4 multiplied by 1 over x squared this x and one of those would cancel and leave me with 4x. So now, if we're just learning this in Calc 1, we would always write out each of these steps. So this is the limit as x approaches infinity of 3 minus the limit as x approaches infinity of 5 over x squared, all divided by the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 4 over x. And then by definition, that is equal to, well, the limit of 3 as x approaches infinity of 3 is just 3 minus, and then this part by this rule is going to be 0, so minus 0 divided by, and then the limit as x approaches infinity of 5 is just 5, and then minus again by that rule, that's going to be 0. So that simplifies to 3 over 5. So that is the basic technique that gets used to evaluate limits as they approach infinity. Now, it's been mentioned about L'Hopital's rule and using L'Hopital's rule. Okay, so let's look at the same problem using L'Hopital's rule. So the limit as x approaches infinity of 3x squared minus 5 divided by 5x squared plus 4x. So to use L'Hopital's rule, I would have to demonstrate that I have infinity over infinity when I applied the limit directly. So this equals infinity over infinity, and maybe some people write it like that. So then I'm going to use L'Hopital's rule, and then that would be the limit as x approaches infinity of 6x divided by, and then 10x plus 4. So that's great, except for the fact that I still have infinity over infinity. So that equals infinity over infinity, and still L'Hopital's rule. And then I have the limit as x approaches infinity of 6 over 10, and that simplifies to 3 over 5. So yes, indeed, I did get the same answer. But it's important to note here that in order to show or demonstrate that L'Hopital's rule would work in both of those cases, the actual proof of that, I need this theorem, right? So some cases, as we know a little bit more about Calculus 1 and taking derivatives, some cases, yes, L'Hopital's rule works just fine. But the only reason L'Hopital's rule works in the first place is because of this very important definition.